Is the profound silence of the universe its greatest lie? We drift through an ocean of night, a void so vast and so quiet that it seems to cradle creation in a state of eternal peace. Out of this darkness we conjure images of breathtaking tranquility. Celestial islands of light adrift and alone, each one a city of stars 100 billion strong. We call them galaxies, and for most of our history we saw them as perfect finished masterpieces spinning in a silent gravitational ballet that has continued undisturbed for eons. Look there at our grand neighbour Andromeda. You can almost feel the majestic slowness of its rotation, a cosmic pinwheel turning once every 250 million years. Its spiral arms, traced by the brilliant blue light of newborn stars and laced with the dark filigree of interstellar dust, are rivers of celestial material flowing in a gentle, predictable current. Each star within that grand design follows its ordained path, a single point of light, contributing to a serene whole, a system in a state of near-perfect dynamic equilibrium. The life of this galaxy, like so many others, we have catalogued seems to be a slow, methodical story of birth and death, of gas collapsing to form stars and of those stars gently returning their elements to the void when their long lives are over. It is a portrait of cosmic order, a universe governed by graceful, comprehensible laws. This is the cosmos we thought we knew, a place of immense scale certainly, but also one of profound reassuring stability. The great spirals like the Whirlpool Galaxy, locked in a delicate tidal dance with its smaller companions, seem to move with the unhurried grace of continents drifting across a planetary surface. The Triangulum Galaxy, a more chaotic but no less beautiful splash of stellar fire, appears as a gentle flurry of creation against the black velvet of space. We built our understanding of the cosmos upon this foundation of quiescence, this assumption that the grand structures of the universe were largely placid, their evolution playing out over timescales that dwarf human comprehension. We learned to read their light to decipher the stories encoded in their ancient photons, and the stories they told were of patience, stories of stellar nurseries slowly igniting, of planetary systems coalescing over millions of years, of the slow, inexorable march of gravity-shaping matter into breathtaking forms. This vision of a peaceful cosmos became deeply ingrained in our consciousness, a comforting notion that for all the chaos on our own small world, the heavens above were a realm of serene mathematical perfection. A clockwork universe wound up at the beginning of time and left to tick with majestic predictability. But this portrait, this grand mural of cosmic serenity that we have so carefully painted across millennia of human observation, is dangerously incomplete. It is a beautiful fiction, a lullaby we sang to ourselves while staring into the dark. Because hidden within some of these seemingly tranquil islands of stars, concealed beneath the familiar gentle glow of their spiral arms, rages a storm of such impossible violence that it defies every intuition we have about the nature of the universe. There are hearts in the darkness that do not beat with a slow, steady rhythm. They roar, they scream, they unleash a torrent of energy so prodigious, so utterly overwhelming, that it can outshine the combined light of every single one of the billions of stars that surround it. The first hints of this terrifying truth were not found in a grand cinematic explosion, but in the quiet, meticulous work of an astronomer in the 1940s. While the world was consumed by terrestrial conflict, a young American scientist named Carl Seyfert was patiently cataloguing the light from the centers of distant spiral galaxies. He was a cosmic cartographer, charting the properties of these remote stellar systems. Most were exactly as expected, their central hubs a dense but ultimately calm concentration of older, yellower stars. But a handful of them, just a small peculiar subset, refused to conform. They were statistical anomalies, outliers in a grand celestial census. In his now famous 1943 paper, a work of humble but revolutionary observation, he noted that a small percentage of spiral galaxies possessed nuclei that were intensely, almost unnaturally bright. They appeared as tiny, star-like points of light, yet they were radiating with an astonishing ferocity. When he passed their light through a spectrograph, breaking it down into its constituent colours, the mystery deepened into a paradox. The resulting spectra, the very fingerprints of the elements within these galactic cores, were unlike anything he had ever seen from a normal collection of stars. A typical galaxy's core shows the blended light of millions of stars a smooth continuum of colour with dark absorption lines where cooler stellar atmospheres have soaked up specific frequencies. It is the signature of a large but fundamentally normal stellar population. The light from Seyfert's peculiar galaxies, however, was utterly alien. On top of the stellar background, his spectra revealed intensely bright broad emission lines. This was not the gentle signature of starlight. This was the unmistakable scream of gas superheated to millions of degrees and moving with terrifying velocity. Imagine the difference between the gentle hum of a perfectly tuned orchestra and a sudden deafening blast of static and feedback. That was the difference between a normal galaxy's core and one of Seyfert's anomalies. The spectral lines were so broad because the gas emitting them was not moving in a gentle ordered rotation. It was being whipped into a frenzy, a gravitational maelstrom of incomprehensible speed. Some clouds of hydrogen and oxygen were rushing towards us at thousands of kilometers per second, while others were simultaneously rocketing away at the same impossible pace. This wasn't the slow dance of stars. This was a cataclysm, a contained, continuous and utterly mysterious explosion happening at the very heart of an otherwise normal-looking galaxy. These galaxies would come to bear his name, Seyfert Galaxies, and they represent a fundamental crack in our peaceful vision of the cosmos. They are the living proof that a galaxy can be two things at once, a serene, sprawling city of stars, and at its absolute centre, a raging, untamable monster. The energy pouring out of a Seyfert nucleus is not stellar. It cannot be explained by even millions of supernova explosions happening at once. The light signature spanning the entire electromagnetic spectrum from low-energy radio waves to the most violent gamma rays points to a physical process far more extreme, a central engine of unimaginable power and efficiency, compressed into a space smaller than our own solar system. Think of the sheer mind-bending absurdity of this scale. You're looking at an object, a galaxy perhaps 100,000 light-years across, containing hundreds of billions of suns, each a thermonuclear furnace in its own right. And yet the entire luminous output of that vast star-filled structure is equalled or even dwarfed by a single infinitesimal point of light burning at its core. It is like discovering a single bacterium on Earth that shines with the light of the sun. It is a physical impossibility, a violation of cosmic proportion, and yet there it is burning in the darkness, a celestial searchlight sweeping across intergalactic space. As our instruments grew more powerful, peering deeper into these active hearts, the mystery only intensified. We discovered there were different types, different flavours of this cosmic madness. Some, which we call Type 1 Seyferts, show us those broad, violent emission lines directly. We are staring right into the blazing, unobscured maw of the central engine. But others, the Type 2 Seyferts, present a more enigmatic puzzle. Their cores are still inexplicably bright, but those frantic broad spectral lines are missing, replaced by calmer, narrower ones. Yet we see evidence of the engine's fury in the cones of ionized gas it blasts out into the surrounding galaxy, like the exhaust from a celestial blowtorch we cannot see directly. It suggests that the monster is still there, but perhaps hidden from our line of sight, its most chaotic light blocked by a thick obscuring shroud of dust and gas. An unblinking eye in one galaxy, a veiled furnace in another. This discovery shattered the illusion of a quiet universe. It forced us to confront a new and unsettling reality that the evolution of a galaxy might not be a gentle, continuous process. It might be punctuated by periods of shocking violence, governed by the whims of a central engine that can switch on and off over millions of years. A Seyfert Galaxy is not a different kind of galaxy. It is a normal galaxy in the grips of a spectacular and perhaps temporary phase of energetic fury. It is a galaxy whose heart has, for reasons we're only just beginning to understand, awakened. And so, the serene portrait of the cosmos is replaced by a far more dramatic, more complex and more compelling one. It raises the most fundamental questions we can ask about the universe we inhabit. What celestial engine, what primordial beast can be small enough to be invisible, yet powerful enough to challenge the light of 100 billion stars? How can such an unfathomable concentration of energy be generated, contained, and unleashed from the gravitational centre of a galaxy? And what does this violent active heart tell us about the galaxy itself? About its birth, its life, and its ultimate fate? To answer these questions, we must journey into the most extreme environment in the known universe. We must leave behind the comforting familiarity of starlight and plunge into a realm governed by forces that bend space-shred matter and accelerate particles to the very edge of light speed. We must look past the tranquil facade of the spiral arms and stare directly into the brilliant, terrifying and awe-inspiring glare of the active galactic nucleus. The answers lie there in the roaring heart of the cosmic storm. It was a world consumed by fire, a planet tearing itself apart. In 1943, humanity's gaze was fixed firmly downwards upon maps of invasion routes, upon the faces of loved ones, sent to distant fronts, upon the smouldering ruins of cities that had stood for 1,000 years. The dominant sounds were the drone of bombers and the crackle of radio propaganda. Amid this global cacophony, a profound silence reigned in the cold, thin air atop Mount Wilson in California. Here, under the immense star-dusted canopy of the Pacific night, one man was looking up, searching for a different kind of conflict, one waged on a scale so vast it defied all human comprehension. His name was Carl Keenan Seyfert, a young, meticulous astronomer from the Yerkes Observatory, on a fellowship at the very pinnacle of his field. He was a man possessed by a quiet intensity, driven not by the headlines of war, but by a deep, abiding need to understand the grand architecture of the cosmos. The instrument at his command was the legendary Hooker telescope, a 100-inch behemoth of steel and glass that had, in the hands of Edwin Hubble, redrawn the map of existence itself, revealing a universe of countless galaxies scattered like dust beyond our own. But Seyfert wasn't looking for new galaxies. He was looking for oddities within the ones we already knew. He was a cosmic pathologist searching for anomalies in the grand serene order of the heavens. In the darkened dome, surrounded by the faint hum of motors and the sharp scent of ozone, he worked with a patience bordering on religious devotion. His canvas was not cloth, but a fragile glass photographic plate coated in a sensitive chemical emulsion. Night after night he would guide the colossal telescope, a gravitational gyroscope pivoting on the Earth's axis to track a chosen spiral galaxy. For hours, the telescope's great mirror would gather the faint ancient light, focusing photons that had travelled for millions of years onto a single tiny square of glass. The process was a delicate art, a communion between astronomer and machine. A slight tremor, a passing cloud, a miscalculation of a fraction of a second, and the precious data would be lost forever, the message from the distant universe hopelessly blurred. After the long cold exposure, the plate would be carefully developed in a dark room, the faint smudges of light emerging like ghosts from the chemical bath. It was on these plates, in the quiet solitude of his analysis, that Carl Seyfert began to notice something profoundly strange. He was conducting a survey, a systematic study of the light coming from the very hearts of distant spiral galaxies. Most were what you would expect, what Hubble and his contemporaries had already documented. They were beautiful, predictable systems. At their centres, a gentle spherical bulge of old yellow stars, a serene concentration of mass and light that gradually faded into the magnificent sweep of the spiral arms. The core of a typical galaxy was a place of settled grandeur, a celestial metropolis in its golden years. But a handful of the galaxies on Seyfert's plates refused to conform. They were rebels. They were misfits. Looking at their photographic portraits, your eye was immediately drawn to the centre, not because of a gentle glow, but because of a blinding, ferocious point of light. It wasn't a bulge, it was a beacon. An impossibly bright, almost star-like nucleus that burned with an intensity that seemed to defy the laws of physics. It was as if someone had placed a celestial blowtorch at the heart of an otherwise normal, pinwheeling city of stars. In some of these images, this single tiny point of light was so brilliant that it threatened to outshine all the hundreds of billions of other stars in the galaxy combined. It was a glaring cosmic overexposure, a physical impossibility that was nonetheless staring back at him from the developed plate. This was the first clue, the first whisper of a revolution. But a bright light, however mysterious, was only a picture. To truly understand its nature, to dissect its message, Seyfert needed to do more than just photograph these galaxies. He needed to break their light apart. He needed to read their chemical signatures. And for that, he turned to the spectrograph, an instrument that would transform his peculiar curiosity into one of the most enduring mysteries in modern astronomy. Imagine starlight as a pure white chord of music containing all the notes of the rainbow blended together. A spectrograph is like a prism that can unplay that chord, spreading the light out into its individual notes, its constituent colours. This resulting band of colours, the spectrum, is not smooth. It is crossed by dark and bright lines, a kind of cosmic barcode. Each line corresponds to a specific chemical element, hydrogen, helium, oxygen, glowing or absorbing light at a precise wavelength. This spectral barcode tells you what a distant object is made of, how hot it is, how fast it's moving. It is the Rosetta Stone for translating the language of light. Seyfert painstakingly attached the spectrograph to the Hooker telescope and began to analyse the light from the blazing hearts of his unusual galaxies. When he developed the resulting spectral plates, the mystery deepened into a profound paradox. The spectra were unlike anything he had ever seen from a galactic core. The barcodes were not just present, they were screaming. The spectra from these brilliant nuclei showed emission lines, bright lines indicating the presence of hot glowing gas. This in itself was not unheard of. Nebulae where new stars are born show such lines. But these lines were different. They were grotesquely broad. A normal narrow spectral line is like a precisely drawn mark, a thin, sharp signature of an element. The lines Seyfert saw were smeared, thickened and stretched out across a wide range of wavelengths. There is only one thing in the universe that can do that to a spectral line extreme velocity. The atoms of gas emitting this light were not moving in some gentle, stately orbit. They were caught in a maelstrom. Some of the gas was rushing towards us at incredible speed, while other parts were flying away just as fast, causing the light to be Doppler shifted simultaneously to the blue and red ends of the spectrum. The result was a single broadened line that told a story of unimaginable violence. When Seyfert did the calculations, the numbers were staggering, almost unbelievable for 1943. The gas clouds in these galactic cores were moving at thousands of kilometers per second, not per hour but per second. Speeds that represented a significant fraction of the speed of light itself. This was not the gentle rotation of a galaxy. This was a sustained, controlled explosion, an engine of incomprehensible power contained within a space no larger than the brilliant point of light he had first seen on the photographs. The core of a normal galaxy was a quiet place. This was a tempest. He had found a new class of object. In 1943, he published his seminal paper, a quiet scholarly work whose title belied the explosive nature of its contents, Nuclear Emission in Spiral Nebulae. In it he listed 6 galaxies that shared these bizarre characteristics, a blindingly bright compact nucleus, and a spectrum filled with unnaturally broad emission lines. They would soon become known to the world as Seyfert Galaxies, and with their discovery the universe suddenly became a much stranger, more violent and more mysterious place. The paper landed in the scientific community like a stone tossed into a still pond. The observations were impeccable. Carl Seyfert was known for his precision. The data was undeniable, but the explanation, there was none. Astronomers were utterly baffled. What conceivable energy source could produce this much light from such a small volume? And what engine could accelerate vast clouds of gas to such lunatic speeds? The known physics of the era offered no answers, only dead ends. Could it be an unprecedented collection of stars, a hyperdense star cluster? Packed shoulder to shoulder at the galactic centre, the calculation simply didn't work. To generate that much light, you would need so many stars crammed into such a tiny space that they would have long ago collided and merged into a single monstrous object, unlike anything ever theorized. There wasn't enough room. Perhaps then it was a chain reaction of supernova stars exploding one after another like a string of firecrackers. This too was a tantalizing but ultimately flawed idea. A supernova is a fleeting event, a momentary flash of brilliance that fades over weeks or months. The light from Seyfert nuclei was constant, a relentless, unwavering glare that had likely been burning for millions of years. This was no firecracker. It was a furnace, a stable and enduring source of power. The mystery presented a fundamental challenge to our understanding of a galaxy's life. To truly appreciate the shock of Seyfert's discovery, you must first picture the universe as we thought we knew it. Picture a normal galaxy one like our own Milky Way or the Great Spiral in Andromeda. From a distance, it is a portrait of cosmic serenity, a majestic pinwheel of light and dust turning slowly in the void. Its heart, the central bulge, is a vast quiet sphere of ancient stars, a golden haze where the stellar orbits are randomized like a swarm of bees. This is the old city, the established center, glowing with the gentle accumulated light of billions of suns that have been shining for eons. The light from this core is soft stellar light. If you were to take its spectrum, you would see the familiar absorption lines of countless cool stellar atmospheres, a composite fingerprint of a mature, stable population of stars. The spiral arms swirling out from this center are the vibrant suburbs regions of active star formation. Here, giant clouds of hydrogen gas collapse under their own gravity, giving birth to brilliant hot young blue stars. These stellar nurseries are beautiful and dynamic, but their energy is localized, spread out across tens of thousands of light years. A normal galaxy is a vast decentralized system, its energy generated by countless individual stars scattered across its immense volume. It is a system in equilibrium, its stately rotation governed by the gentle collective pull of gravity. It is predictable. It is understandable. Now cast that image aside. In its place, picture one of Carl Seyfert's bizarre creations. From a distance, it looks much the same spiral arms, the same dusty lanes. But as you approach the center, the peaceful golden haze is gone. In its place is a single, searing point of light, a star-like nucleus that burns with the ferocity of a quasar yet is embedded within an otherwise ordinary-looking galaxy. This core is not a collection of stars, it is an event. It is an engine. The light pouring from this compact region is not the gentle thermal glow of stars. It is a torrent of high-energy radiation, a continuous blast of X-rays and ultraviolet light that ionizes everything around it. The spectrum tells you that this is not a place of equilibrium. It is a region of pure chaos where clouds of gas larger than our solar system are being torn apart and flung outwards at velocities that mock the galaxy's own gravitational field. The Seyfert nucleus was not just a brighter version of a normal galactic core, it was a different phenomenon entirely. It was as if in the heart of a quiet, sprawling city someone had ignited a fusion reactor the size of a city block. It broke the rules. It shattered the serene portrait of the cosmos that astronomers had so carefully assembled. For decades, Seyfert's discovery would remain an enigma, a loose thread in the tapestry of astrophysics. It was a footnote in textbooks, a curiosity for specialists, because no one had a plausible explanation for what was happening. The energy required was simply too immense, the source too compact. It hinted at a form of energy production far beyond nuclear fusion, something more efficient, more violent, more fundamental. Carl Seyfert had not set out to start a revolution. He was a cartographer carefully mapping the known territories of the cosmos. But in his meticulous work, he had stumbled upon the shores of an entirely new continent of physics. He had discovered a signpost pointing toward a phenomenon whose existence was in 1943 still confined to the most esoteric realms of theoretical mathematics. He had found evidence of a monster lurking in the dark heart of the universe, a gravitational ghost whose true nature was more fantastic and more terrifying than anyone of his generation could possibly have conceived. The question he posed with his photographic plates would echo through the halls of astronomy for half a century. What is lighting the fire in the heart of a Seyfert galaxy? Finding the answer would require a new generation of telescopes, a new way of seeing the universe, and the courage to imagine an object so extreme it could literally tear a hole in the fabric of space-time itself. The journey into that active, violent heart had only just begun. For 2 decades, the puzzle Carl Seyfert had left behind remained a ghostly impression on photographic plates, a whisper of strange light confined to the optical world. It was a mystery for the eyes alone. The bright star-like hearts of these galaxies were an enigma, but an enigma contained within the familiar spectrum of visible light, the same narrow window our own biology granted us. Science, however, was on the cusp of evolving new senses. Humanity was about to learn how to listen to the universe, to perceive its most violent fevers, and in doing so to transform Seyfert's puzzle from a curious astronomical footnote into a profound crisis, that would shake our understanding of galaxies to their very core. The revolution began not with a lens, but with an antenna. Throughout the 1960s, a new generation of colossal instruments began to unfurl across the quiet landscapes of Earth. Great steel dishes hundreds of feet across, turning their gaze to the heavens, blind to the starlight that had guided humanity for millennia. These were the cathedrals of radio astronomy, and they were tuned to a completely different cosmic frequency, a deeper invisible hum underlying the visible cosmos. When these new ears were pointed towards Seyfert's peculiar galaxies, the faint whisper of mystery became a deafening roar. They were anything but quiet. In the radio spectrum, these galactic cores were incandescent, shouting into the void with an energy that made no sense. This wasn't the gentle thermal radio hiss you would expect from warm clouds of interstellar dust or the combined glow of stars. That would be like the background murmur of a distant city. This was something else entirely. It was a sharp, piercing signal with a unique electronic signature, a form of light known as non-thermal or synchrotron radiation. And recognizing it was like a detective finding a spent casing from an impossible weapon at a crime scene. Synchrotron radiation is not the byproduct of heat. It isn't born in the heart of a star or a warm nebula. It is the scream of electrons whipped up to nearly the speed of a light and then violently wrenched around by powerful magnetic fields. Imagine a subatomic particle, a tiny speck of matter accelerated to a velocity where time itself begins to warp. Now imagine that particle being snared in a magnetic web, forced into a dizzying spiral, a cosmic pirouette on a knife's edge. With every turn it bleeds energy, flinging off radio waves like sparks from a grinding wheel. To produce the sheer volume of radio light seen from Seyfert cores, you don't just need a few stray electrons. You need a full-blown particle accelerator of galactic proportions. Something in that tiny unresolved nucleus was acting as a dynamo, a celestial cyclotron creating magnetic fields of ferocious intensity and using them to accelerate matter to the ultimate cosmic speed limit. Suddenly, the starburst theory, the idea that Seyfert cores were merely regions of exceptionally dense and rapid star formation, began to look hopelessly inadequate. 1 billion young hot stars would indeed create a brilliant core. They would heat up gas and dust, causing them to glow. But they could not by any known physics organize themselves into a coherent magnetic engine capable of this feat. Stars are chaotic individual furnaces scattered across light years. The synchrotron emissions spoke of a single unified process, a monolithic source of extraordinary power, marshalling particles and fields with a terrifying coherence. The evidence was becoming incontrovertible. The light from a Seyfert nucleus was not the sum of many small fires. It was the blast from a single celestial blowtorch. This discovery fundamentally altered the question astronomers were asking. They were no longer wondering how many stars were in the core. They were now forced to ask the far more disturbing question, what was in the core instead of stars? As radio telescopes revealed this magnetic beast, another technological leap was preparing to unveil its fiery breath. For all its power, radio astronomy was still earthbound. But our planet's atmosphere, the very air that gives us life, is an opaque shield, a celestial sensor blocking the most energetic and violent forms of light from ever reaching the ground. To see the true ferocity of the cosmos, we had to leave our world behind. In the late 1960s and early 1970s, humanity sent its first true eyes into orbit. Satellites like Uhuru, the first dedicated X-ray observatory, were not grand telescopes in the traditional sense. They were more like celestial Geiger counters designed to detect the high-energy photons forged in the most cataclysmic events the universe had to offer. X-rays are the light of pure violence. They are produced by matter heated to millions of degrees by shock waves from titanic explosions, and by matter plunging into gravitational wells of unimaginable depth. If visible starlight is the gentle warmth of a campfire, X-rays are the blinding flash of a thermonuclear detonation. And when Uhuru and its successors turned towards the Seyferts, they found that these galactic hearts were not just radio loud. They were blazing infernos of X-ray radiation. The sheer luminosity was staggering. A single tiny point in the center of a galaxy like NGC 4151 was pumping out more X-ray energy than 100 billion suns combined. This was a death blow to any lingering conventional explanation. No collection of stars, no matter how numerous or massive, could generate this kind of high-energy furnace. Heating gas to millions of degrees requires an energy source so concentrated, so efficient, that it defied all astronomical precedent. The picture was becoming clearer and infinitely more terrifying. In the core of a Seyfert galaxy, there was a central engine generating organized magnetic fields for its radio voice, and simultaneously superheating a vast corona of surrounding gas to temperatures hotter than the core of our own sun, creating a beacon of X-rays that could be seen across millions of light years. This was not a place. It was a condition, an extreme physical state that had no analogue in our own placid galaxy. By the mid-1970s, we had a multi-wavelength portrait of the culprit. We could see its brilliant, chaotic light in the optical spectrum. We could hear its magnetically powered scream in the radio, and we could feel its furious heat in the X-rays. Each new window we opened onto the universe revealed another layer of its impossible power. Yet for all this newfound knowledge, the central mystery only deepened because every observation pointed to one inescapable conclusion. Whatever this engine was, it had to be impossibly small. This is where the most powerful clue of all emerged, and it came not from a new technology but from an old practice patience. Astronomers began to monitor these Seyfert cores night after night, year after year, and they discovered something utterly mind-bending. The light flickered. The brilliant nucleus wasn't a steady flame, it was a sputtering candle. Over the course of months, sometimes just weeks, the entire energy output of the core, a luminosity dwarfing that of the hundreds of billions of stars in its host galaxy, would rise and fall dramatically. The X-ray flux would double. The optical light would flare. This variability was the smoking gun. Consider the simple logic imposed by the universal speed limit, the speed of a light. Imagine a luminous object that is 1 light year across. If that object were to suddenly brighten all at once, the light from the nearest side would reach you immediately, but the light from the far side would take a full year longer to arrive. From your perspective, the object would appear to brighten gradually over the course of a year. It cannot physically flicker any faster than the time it takes light to cross from one side to the other. Its size therefore sets a maximum speed for its variability. The Seyfert Galaxies were observed to vary over timescales of months. This meant that the source of this colossal energy, the engine outshining 100 billion stars, could be no larger than a few light months across. That is an astonishingly claustrophobically small volume. It's a space roughly the size of our solar system, and that changed everything. You simply cannot pack 100 billion stars into a space the size of the solar system. It's physically impossible. Furthermore, you cannot choreograph 100 billion stars to all brighten and dim in near-perfect unison over a few weeks. It would be like expecting an entire city's population to sneeze at the exact same instant. The rapid variability was the final incontrovertible proof that the engine was not a collection of objects but a single object, a solitary compact behemoth, a gravitational monster residing in the absolute centre of the galaxy, governing its behaviour with an iron fist. The scientific community was now grappling with a heretical idea. Galaxies long thought to be serene islands of stars' majestic clockwork systems, governed by the gentle collective pull of their stellar populations, might actually be fundamentally different. Their evolution, their structure, their very nature, could be dictated by a central anomaly, a singular phenomenon of such extreme physics that it bordered on the supernatural. Alternative theories were proposed, each more exotic than the last. Perhaps it was a spinar, a hypothetical supermassive rapidly rotating star stabilized against collapse by its own magnetic fields. Or maybe a dense cluster of pulsars or stellar mass black holes all colliding and merging in a chaotic gravitational mosh pit. But each of these ideas eventually buckled under the weight of the evidence. None could adequately explain the sheer power, the specific light signatures across the entire electromagnetic spectrum, and the coherent variability all at the same time. The evidence was pointing not to an exotic type of star, or even a cluster of dead ones. It was pointing to something far more fundamental. Something predicted by the mathematics of Einstein, but which many physicists still considered a mathematical ghost, a monstrous abstraction too terrible to actually exist in reality. By the dawn of the 1980s, the case file was thick with clues. The perpetrator was compact, no larger than our solar system. It was prodigiously powerful, outshining its entire host galaxy. It was a master of extreme physics, accelerating particles to near-light speed, while simultaneously heating gas to millions of degrees. And it was a singular entity acting as one. Astronomers had built a perfect detailed outline of the monster, but its true identity remained in the shadows. The hunt for Carl Seyfert's enigmatic points of light had led science to the threshold of a new cosmology, to the edge of an abyss in our understanding of matter, energy, and gravity. The evidence no longer described a place you could visit or an object you could see. It described a rupture in the very fabric of space-time itself, a point of no return from which not even light could escape. The stage was set for the ultimate revelation. The evidence had become a chorus of contradictions. For decades, we had been meticulous collectors of cosmic paradoxes, gathering light from the hearts of these strange luminous galaxies. We found a celestial glare that could outshine 1 trillion suns, but it emanated from a space no larger than our own solar system. We measured gas clouds screaming through the void at impossible speeds, yet somehow held captive by a force we could not see. The puzzle pieces were strewn across the table of astronomy, glinting with tantalizing clues, but they refused to fit. They seemed to belong to a dozen different boxes describing objects that were simultaneously vast and compact, ancient and violent orderly in their galactic spiral, and utterly chaotic at their core. Every new observation only tightened the knot. The sheer power density was the greatest stumbling block and affront to conventional physics. No known stellar process, not even a frenzy of millions of supernovae detonating in unison, could generate that much energy in such a confined volume and sustain it for millions of years. The engine, whatever it was, had to be something else entirely. It had to be compact, incredibly massive, and ruthlessly efficient at converting matter into raw radiant energy. The solution, when it began to emerge, felt less like a discovery and more like a surrender to the inevitable, a reluctant acknowledgement of the most extreme object predicted by our most profound theory of gravity. It began not with a photograph, but with a whisper of an idea born from the deepest and most disturbing implications of Einstein's relativity, the idea of a black hole, and not just any black hole. The kind that forms from a dying star a few times the mass of our Sun would be a mere speck of dust next to the Titan required. The hypothesis was far more audacious, a monster lurking in the dark, a supermassive black hole with the mass of millions or even hundreds of millions of suns. At first, the concept was met with profound skepticism. These objects were theoretical phantoms, mathematical curiosities born from equations pushed to their absolute limits. To propose one as the central engine of a Seyfert Galaxy seemed like invoking magic to explain a mystery. But as the calculations were refined, the idea began to take on a terrifying logic. Only the gravitational authority of such a behemoth could anchor gas clouds, moving at a fraction of the speed of light. Only a gravitational well that deep could provide the raw power needed to fuel the observed luminosity. The model was no longer just a possibility, it was the only candidate that could withstand the onslaught of contradictory evidence. It was the only key that seemed to fit the impossibly complex lock. So how does this invisible Leviathan generate such a spectacular display of light? A supermassive black hole is not a cosmic vacuum cleaner indiscriminately devouring everything in its path. Its power comes not from what it consumes, but from the agonizingly slow and violent process of consumption. Imagine a star or a vast cloud of interstellar gas wandering too close to the galactic center. It is captured not in a single gulp, but by the relentless, inescapable pull of gravity. It cannot fall straight in. Instead, like water spiraling down a drain, it is pulled into a vast orbiting structure, a swirling maelstrom of matter known as an accretion disk. Here you must erase any image of a serene planetary ring. This is a place of unimaginable violence. It is a cosmic grindstone, a city-sized traffic jam, where orbits decay and matter smashes together at blistering speeds. The disk is a flattened rotating platter of plasma, perhaps light years across at its tenuous edge, but compressing and accelerating as it nears the central abyss. Every particle in this disk, from a single hydrogen atom to the shredded remains of a sun, is on a one-way journey. As it spirals inward, it is subjected to cataclysmic frictional and viscous forces. gas streams rub against each other, generating immense heat through a process of gravitational friction. Orbits are squeezed, compressing the material to incredible densities and temperatures. Gravitational potential energy, the most powerful energy source in the universe, is being converted into thermal energy with ruthless efficiency. The outer regions of the disk, still relatively cool, might glow with the familiar visible light we see with our telescopes. But as we move inward, closer to the point of no return, the temperatures skyrocket. A few light days out, the disk is hot enough to glow fiercely in ultraviolet light, a searing blue-white blaze that becomes a dominant feature of the Seyfert's light signature. Closer still, in the final frantic orbits just before the event horizon, the plasma is heated to millions of degrees. Here matter is so energized that it emits a shriek of high-energy X-rays radiation, powerful enough to penetrate deep into the cosmos. This structure, this gravitational furnace, is the engine we were looking for. It explains the sheer unbridled luminosity. The conversion of mass into energy within an accretion disk can be more than 10 times more efficient than nuclear fusion, the process that powers the stars. For every kilogram of matter that falls through the disk, a significant fraction of its mass is converted directly into the radiant energy we observe. This is what allows a region no bigger than our solar system to outshine an entire galaxy of 200 billion stars. It also exquisitely explains the spectral signatures that had puzzled us for so long. The broad emission lines, those smeared-out fingerprints of hydrogen and helium, were the definitive proof of this model. They are the battle cries of gas clouds trapped within the disk's ferocious spin. Some parts of the disk are rotating towards us, some away. This rapid motion approaching a significant fraction of the speed of light causes an extreme Doppler shift. The light from gas moving towards you is compressed, shifted to the blue end of the spectrum. The light from gas moving away is stretched, shifted to the red. When we look at the disk as a whole, we don't see one sharp emission line. We see the combined light from all of that fast-moving gas, at once a composite signal that is smeared or broadened into the exact signature that Carl Seyfert first recorded. The mystery of the broad lines was solved. They were a direct measurement of the orbital velocities in the throat of a monster. But science is never so simple. Just as one great mystery was solved, another more subtle puzzle took centre stage. We had a powerful cohesive model for the Seyfert engine. Yet when we looked out at the universe, we still saw what appeared to be two fundamentally different types of Seyfert galaxies. There were the Type 1s, the classic examples, which showed both the broad and narrow emission lines. They were the ones whose light varied erratically, flickering and flaring on timescales of days or weeks, a clear sign of a compact turbulent central region. Then there were the Type 2s. These galaxies possessed the bright cores, and they had the narrow emission lines, but the broad lines were conspicuously absent. Their light was far more stable, lacking the wild variability of their Type 1 cousins. For years they were classified as a separate, perhaps less energetic or fundamentally different kind of active galaxy. It was as if we'd discovered a single species of magnificent celestial lion, but found that some roared with full-throated power, while others only produced a muted, filtered growl. Were they truly different beasts, or were we failing to understand something fundamental about how we were observing them? The answer when it came was a masterpiece of scientific elegance and simplicity. It didn't require a new engine, but a new perspective. It is an idea known today as the Unified Model of Active Galactic Nuclei, and it proposed that the difference between a Type 1 and a Type 2 Seyfert was not a difference of substance, but of orientation. It was all a matter of our viewing angle. The model hypothesized that the supermassive black hole and its luminous accretion disk are not sitting naked in the center of the galaxy. Instead, they are surrounded by a thick opaque donut-shaped structure of cool gas and interstellar dust, a feature we now call the dusty torus. This torus orbits the central engine but on a plane perpendicular to the accretion disk itself. It is not part of the hot glowing and falling material. It is a vast obscuring shroud, a cosmic veil that dictates what we are allowed to see. This structure is essential. It acts like a lampshade around a blindingly bright bulb, absorbing the direct light from the accretion disk and blocking our view from certain angles. Now picture yourself as a cosmic observer, looking at this central engine from different vantage points in the universe. If your line of sight happens to be looking down from above or up from below the plane of this dusty torus, you have a clear, unobstructed view. You are staring directly into the brilliant, chaotic heart of the machine. You can see the searing, hot inner regions of the accretion disk. You can witness the high-velocity gas clouds that produce the famous broad emission lines. You see the rapid, unpredictable flickering of the central source as instabilities ripple through the disk. From this privileged perspective, you're seeing a Seyfert Type 1 galaxy in all its raw and unfiltered glory. You're witnessing the engine's roar. But what if your cosmic vantage point is different? What if your home galaxy, our Milky Way, is aligned such that you're looking at the Seyfert's central engine edge-on? From this angle, the thick, dusty torus lies directly in your line of sight. It becomes an impenetrable wall. You can no longer see the central engine. The brilliant accretion disk is completely hidden from view. The broadline region with its frenzied gas clouds is also obscured behind this wall of dust. The broad emission lines, the smoking gun of the spinning disk, vanish from your spectrum. You're completely blind to the direct fury of the black hole's feasting. However, you are not in total darkness. While the direct light is blocked, some of it escapes vertically, shooting out from the top and bottom of the torus like beams from a cosmic lighthouse. This light travels far out into the host galaxy, eventually striking slower-moving, more distant gas clouds, the narrow line region. These clouds absorb and re-emit that light, scattering it in all directions. Some of that scattered second-hand light travels towards you. What you see, therefore, is not the engine itself, but the echo of its power reflected off distant clouds. You see the narrow emission lines produced by this slow-moving gas, but you miss the broad lines entirely. The variability is gone, smoothed out by the vast light travel time across these larger regions. From this obscured perspective, you are seeing a Seyfert Type 2 galaxy. Suddenly, with this single powerful idea, the chaos resolved into pristine order. The two seemingly distinct classes of Seyfert galaxies were not two species at all. They were one and the same. A Type 2 is simply a Type 1 that is hiding its face from us. The model also made a stunningly precise prediction. If this dusty torus was absorbing all that direct energy from the accretion disk, it must heat up, and anything that heats up must radiate that energy away. The calculations showed that the dust in the torus should glow brilliantly, not in visible light, but in the infrared portion of the spectrum. When our infrared telescopes turned their gaze towards Type 2 Seyferts, they found exactly that, a colossal source of infrared radiation, the telltale heat signature of the hidden obscuring donut. It was the final triumphant confirmation. The unified model was less a theory and more a key unlocking a door that had been sealed for half a century. It was a profound lesson in cosmic humility, a reminder that what we see is so often dictated by where we stand. The universe, it turned out, was not presenting us with two different puzzles, but was simply showing us two different sides of the same magnificent, terrifying, and now finally understandable engine. The roars and the growls were emanations of the same beast, and so the engine is laid bare. A gravitational singularity, a point of infinite density veiled by an event horizon, surrounded by a maelstrom of matter heated to millions of degrees. It is a spectacle of cosmic violence, a beacon of ferocious energy shining from the heart of a galaxy. But to see this supermassive black hole merely as a furnace, an endpoint for unfortunate stars and gas, is to miss the greater, more profound truth. The revelation of the engine is not the end of the story. It is the beginning of an entirely new understanding of what a galaxy is. For this central monster is not a passive feature, a simple drain at the center of a cosmic sink. It is an active, breathing, and profoundly influential partner in a celestial dance that spans billions of years. The black hole does not just consume its host, it communicates with it, argues with it, and ultimately shapes its very destiny. This conversation, written in fire and gravity, is known by a simple, almost clinical name, feedback. But there is nothing simple about it. It is the complex, often contradictory process that links the smallest point in the galaxy to its grandest structures, a mechanism that can both give life and command death on an unimaginable scale. To understand this cosmic feedback loop, you must first reimagine the accretion disk. It is not just a glowing drain. It is the most powerful particle accelerator and the most luminous blowtorch in the known universe. The light it produces, the sheer radiation pressure pouring out from this swirling vortex of superheated plasma, is a physical force. This light is a wind, an ethereal yet unstoppable hurricane of high-energy photons and charged particles, blowing outwards from the galactic core at a significant fraction of the speed of light. This is not a gentle breeze. Imagine a relentless galaxy-sized sandblaster scouring everything in its path. As this galactic wind surges through the central regions of the Seyfert Galaxy, it collides with the vast, cold, serene clouds of molecular gas that drift between the stars. These clouds are the galaxy's future. They are the stellar nurseries, the reservoirs of raw material from which new generations of stars are meant to be born. In a quiet, ordinary galaxy, these clouds would slowly cool contract under their own gravity and eventually collapse to ignite into brilliant new suns. But here in the tempestuous heart of a Seyfert, their fate is violently rewritten. The wind from the active nucleus slams into these clouds with brutal efficiency. It heats them, energizing their atoms until they can no longer remain gravitationally bound. The delicate process of stellar conception is aborted before it can even begin. The gas that would have formed millions of suns is instead stripped away, ionized, and pushed out of the galactic plane, altogether exiled into the desolate void of intergalactic space. We can see the evidence for this galactic exodus carved into the spectrum of light from these galaxies. We see the spectral signatures of elements like oxygen and neon not sitting still where they should be, but blue shifted towards us, or red shifted away, clear evidence of gas being violently ejected at thousands of kilometers per second. This is the black hole acting as a galactic sterilizer. It's a process we call negative feedback or quenching, and it is one of the most important forces in the universe. It is the mechanism by which a black hole, an object that occupies an infinitesimally small volume, can dictate the fate of a structure hundreds of thousands of light years across. It establishes a galactic thermostat. If too much cold gas flows towards the center, the black hole and its accretion disk flare up, launching these powerful winds that clear out the fuel supply, shutting down star formation and its own growth in the process. The galaxy is effectively preventing itself from burning out too quickly, regulated by the very monster it feeds. But radiation pressure is only one half of this story. For a select few, the most powerful Seyferts, the feedback mechanism, becomes even more spectacular, more focused, and more terrifyingly potent. As matter swirls in the final moments of its existence within the accretion disk, extreme magnetic fields twisted and amplified by the black hole's rotation can act as a colossal cosmic cannon. These fields ensnare charged particles from the disk, and in a process still not fully understood, accelerate them away from the poles of the black hole in two perfectly collimated needle-thin beams. These are relativistic jets. They are fountains of plasma moving at over 99% of the speed of light, coherent structures that can travel for millions of light years, far beyond the visible boundaries of their host galaxy. When these jets tear through the interstellar medium of their own galaxy, the effect is cataclysmic. They are not like the wide-fronted push of the radiation winds. They are surgical, immensely powerful drills. They punch clean through the galactic disk, creating vast tunnels and inflating enormous radio-emitting lobes of superheated plasma in the galaxy's halo. Imagine pouring water into a mound of loose sand. It seeps in, gently saturating the material. That is the slow gravitational collapse of gas that forms stars. Now imagine firing a pressure washer into that same mound of sand. The sand is blasted away, scattered into a chaotic, turbulent mess. That is the effect of a relativistic jet. The immense kinetic energy carried by the jet is deposited into the surrounding gas, heating it to millions of degrees. This creates a vast enveloping bubble of hot, low-density gas around the galaxy. This cosmic cocoon acts as a barrier preventing any new cold gas from the intergalactic medium from falling into the galaxy and replenishing its star-forming reservoirs. The galaxy's supply lines are cut. Star formation is not just paused, it is starved into submission over cosmological timescales. This is quenching on a grand scale a long-term regulation that can fundamentally alter a galaxy's evolutionary path, transforming it from a vibrant blue star-forming spiral into a red, dormant and dying elliptical. The black hole has not just trimmed the hedges, it has salted the earth, ensuring nothing new can grow for eons to come. This powerful destructive influence is the clearest evidence we have that the central engine and its host galaxy are locked in a battle for resources, a self-regulating cycle of feast and famine that defines the galaxy's entire life. And yet, if this were the only interaction, the universe would be a far more barren place. A story of pure destruction is too simple, too one-dimensional for the cosmos. The universe in its infinite complexity has woven a stunning paradox into the heart of this galactic violence. The very same mechanisms of feedback that quench and sterilize can, under the right circumstances, become the catalyst for creation. The same cosmic storm that brings drought can also, in its passing, trigger a deluge of new life. This is the theory of positive feedback, a beautiful and counterintuitive twist in our story. Consider again the powerful outflows, those hurricanes of radiation and plasma, expanding outwards from the active nucleus. We have seen them as destroyers, heating and dispersing the cold gas clouds. But what happens at the leading edge of this expanding shockwave? As this bubble of hot gas inflates and pushes its way through the galaxy, it acts like a cosmic snowplow. It sweeps up the ambient interstellar gas, compressing it into dense shells and filaments at the shock front. Here in this zone of compression, the conditions can become perfect for a new generation of stars. The gas density is increased dramatically, far beyond what gravity alone could achieve in the same time frame. This intense squeezing can be the final push needed to trigger a gravitational collapse within these newly formed dense clouds. The shockwave from the black hole's outburst, the very agent of destruction, becomes the midwife to a furious burst of starbirth. We see this happening. With our most powerful telescopes, we can map the intricate relationship between the expanding radio lobes carved by jets and the location of young, massive blue stars. Often, we find these stellar nurseries wrapped around the edges of the hot plasma bubbles like pearls strung along the edge of a void. It is a breathtaking sight, a wall of fire that ignites new suns even as it carves a path of devastation through the galactic heartland. The black hole gives with one hand what it takes away with the other. One region of the galaxy is rendered inert, its gas heated and blown away, while another caught in the compressive shockwave erupts into a brilliant short-lived blaze of glory. This duality reveals a far more intricate and nuanced relationship between the central engine and its host. It is not a simple thermostat. It is a celestial sculptor chiseling away at some parts of the galaxy, while compacting others into new and beautiful forms. This intricate dance of creation and destruction, of positive and negative feedback, leads us to the most profound conclusion in modern astrophysics: the coevolution of galaxies and their central black holes. For decades, these were treated as separate phenomena. A galaxy was a vast collection of stars, gas and dark matter, and a black hole was a curious compact object that happened to reside at its centre. There was no reason to suspect they were intimately connected. A supermassive black hole, for all its immense mass, is gravitationally dominant over only the very innermost few light years of a galaxy. The galaxy itself is trillions of times more massive and millions of times larger. Why should the properties of the whole be so tightly linked to the properties of this tiny central point? And yet they are. When astronomers plotted the mass of a galaxy's central black hole against the mass of its central bulge of stars, they found a stunningly tight correlation. Galaxies with bigger bulges had bigger black holes. Galaxies with smaller bulges had smaller black holes. This relationship, known as the M-sigma relation, holds true across the universe for galaxies of all shapes and sizes. This cannot be a coincidence. It is cosmic scripture telling us that these two entities, the microscopic nucleus and the macroscopic galaxy, somehow grew together. They must have communicated throughout their lives, regulating each other's growth in a lockstep process that spans billions of years. Feedback is the language of that communication. Imagine the early universe. A young proto-galaxy is rich with pristine hydrogen and helium gas. This gas flows inwards, feeding two processes simultaneously. It forms new stars in the galaxy's bulge, and it fuels the growth of the seed black hole at its centre. For a time, they grow together in harmony. The bulge gets bigger, the black hole gets heavier. But as the black hole grows, its power, its feedback grows exponentially. At a critical threshold, the black hole becomes so massive and so luminous that its winds and jets become powerful enough to halt the inflow of gas. The feedback effectively scours the galaxy clean of fuel. In doing so, it chokes off its own food supply and simultaneously halts the formation of new stars in the bulge. The growth of both the black hole and the bulge stops. They are frozen in place, their relative masses locked into the precise ratio we observe today. This symbiotic relationship, this gravitational pact, is the engine of galaxy evolution itself. It explains why we see so many red and dead elliptical galaxies in the universe today. These are likely the descendants of ancient Seyferts or quasars, whose central black holes grew so powerful they effectively shut down their entire galaxy, leaving behind a fossil collection of old red stars. The Seyfert phase, then, is not just a curiosity. It is a crucial transformative chapter in a galaxy's life. It is the turbulent adolescence during which the galaxy and its black hole wrestle for dominance, a conflict that ultimately sets the course for the galaxy's entire future. It determines its size, its shape, its colour, and its ultimate fate. We are not just looking at a bright galactic core. We are witnessing the very process that builds the cosmic structures we see around us. Each Seyfert galaxy is a laboratory where we can watch the laws of physics sculpt matter on the grandest of scales, forging the universe we inhabit today. The light from its core is more than just a beacon. It is the echo of a conversation between a galaxy and its heart, a conversation that decided whether it would live a long quiet life or blaze brightly and die young. This cosmic symbiosis is not just a feature of galaxies, it is the very reason they are what they are. For so long, these furious hearts remained ghosts in our theories. We had drawn the maps we had written, the equations we had imagined, the swirling vortex of an accretion disk, and the great dusty shroud of the torus. We had conceived of a central engine of unimaginable power, yet it was all an act of deduction, an inference drawn from the spectral fingerprints of light that had travelled for millions of years to reach us. The central question, the one that echoed in the halls of astronomy, was painfully simple. Could we ever truly see it? Could we resolve a structure smaller than our own solar system, buried in the blinding glare of a galactic core millions of light years away? It was a challenge of scale so profound it bordered on the impossible. Answering it would require a new generation of eyes, instruments of unprecedented power and precision, capable of peering into the storm. It would demand that we lift our gaze above the shimmering veil of our own atmosphere, or find a way to cancel out its distortions from the ground. The quest was on not just to confirm a model, but to witness the mechanics of cosmic creation and destruction firsthand. The moment had arrived to transform our elegant theoretical blueprints into tangible observed reality. We were about to knock on the door of the monster's lair, armed with mirrors and sensors ready for whatever stared back. Our first true glimpse into these inner sanctums came from orbit, from the unblinking eye of the Hubble Space Telescope. Freed from the blurring effect of Earth's atmosphere, Hubble delivered a clarity that had been the stuff of dreams. For the first time, we could peel back the diffuse glow of the host galaxy's stars and isolate the violent pinpoint of light at its centre. In nearby Seyferts, like the magnificent Circinus galaxy, Hubble's vision pierced through the foreground stars of our own Milky Way, revealing the intricate chaotic tapestry of the active nucleus itself. It unveiled not just a single point of light, but a complex structured environment. We saw vast ghostly cones of ionized gas fanning out from the hidden nucleus for thousands of light years. These were the telltale signatures of the engine's shadow. The dense, dusty torus, our theoretical donut, was blocking the intense radiation in the equatorial plane, allowing it to escape only through the poles like a cosmic lighthouse beam. This escaping radiation, a torrent of X-rays and ultraviolet light, acts as a celestial blowtorch flash, heating the interstellar gas in its path and causing it to glow with incandescent fervour. Hubble imaged these ionization cones with breathtaking detail, their geometry a perfect match for the predictions of the Unified Model. We were not just seeing the light from the engine, we were seeing the illuminated wreckage left in its wake. This was more than just circumstantial evidence. This was the engine's energetic footprint stamped directly onto the fabric of its host galaxy. In cases like NGC 1068, Hubble, combined with other observatories, allowed us to map these outflows in stunning relief, watching as jets of material collimated by powerful magnetic fields slammed into the surrounding gas, creating shock waves that rippled through the galactic disk. The abstract idea of a central engine influencing its surroundings was no longer abstract. We could see the lines of force, the channels of power carved into the very structure of the galaxy. Hubble gave us the context, the grand vista of the Seyfert phenomenon, proving that these were not isolated curiosities but dynamic integrated systems. Yet even with Hubble's sharp vision, the central engine itself, the accretion disk, the swirling maelstrom of infalling matter remained an unresolved point of light, its secrets still tantalizingly out of reach. To push deeper to resolve that final crucial pinprick, we needed to overcome our planet's greatest observational hurdle, its own atmosphere. The very air we breathe, with its turbulent currents and shifting temperatures, acts like a warped lens, blurring starlight and smearing the fine details of the cosmos into a frustrating haze. For decades, this atmospheric distortion meant that even the largest ground-based telescopes could never compete with the sharpness of a smaller telescope in space. But human ingenuity forged a revolutionary solution, a technique so audacious it sounds like science fiction adaptive optics. Imagine a telescope mirror that is not rigid but fluid and alive. A mirror composed of hundreds of tiny piston-like segments, each capable of adjusting its position thousands of times per second. This is the heart of an adaptive optics system. A laser is fired from the observatory, creating an artificial guide star high in the atmosphere. A sensor watches this artificial star, measuring precisely how the atmosphere is distorting its light on a moment-to-moment basis. This information is fed to a supercomputer, which calculates the exact inverse of that distortion and sends commands to the deformable mirror bending its surface to cancel out the atmospheric shimmer in real time. The result is nothing short of magic. The shimmering, blurry image of a distant object snaps into crystal-clear focus as if the atmosphere itself has vanished. Ground-based observatories like the Keck telescopes in Hawaii and the Very Large Telescope in Chile, armed with this celestial Steadicam, could now achieve resolutions even greater than Hubble's in certain wavelengths. The Earth was no longer our prison. It was a stable platform for a new, sharper view of the universe. Now we could truly bring the fight to the galactic core. We could aim these newly focused eyes at the hearts of Seyfert Galaxies and attempt to do something truly extraordinary to weigh the central supermassive black hole. Weighing an object you cannot see, an object from which not even light can escape, sounds like an impossible task. But the universe provides a scale if you know how to read it. That scale is gravity. A black hole, no matter how dark, exerts a colossal gravitational pull on everything around it. By tracking the motion of stars or clouds of gas orbiting the black hole, we can use the fundamental laws of physics first laid down by Johannes Kepler and Isaac Newton to calculate the mass of the central object they are enslaved to. The faster they move and the closer they are to the centre, the more massive the object they are orbiting must be. With the power of adaptive optics, we can now resolve the individual movements of stars perilously close to the galactic centre. We can watch them execute their gravitational dance, whipping around the unseen behemoth at speeds of thousands of kilometers per second. Each star's orbit becomes a data point, a single weight placed on a cosmic balance. By patiently observing these orbits over years, we map the gravitational field with incredible precision. And when the calculations are done, the numbers that emerge are staggering. Not millions, but tens of millions, sometimes hundreds of millions of times the mass of our Sun, all packed into a volume smaller than our solar system. The ghost in the machine now had a number, a physical quantity that spoke of its terrifying power. But there is another, even more ingenious method for weighing these monsters, one that relies not on motion, but on the speed of light itself. It's a technique called reverberation mapping, and it turns the very chaos of the Seyfert nucleus into a precision tool. The accretion disk, that turbulent whirlpool of superheated matter, does not shine with a steady light. It flickers and flares unpredictably like a cosmic storm. These bursts of intense radiation travel outwards in all directions at the speed of light. Surrounding the disk, as our models predicted, are the clouds of gas that make up the broadline region. When a flare from the disk hits these clouds, it energizes them, causing them to light up in response like a fluorescent bulb being switched on. Here is the beautiful trick: we see the initial flare from the disk first. Then there is a time delay before we see the response from the gas clouds, because the light from the flare had to travel from the disk out to the clouds. It is a light echo. By measuring this time delay, which can be days, weeks, or even months, we are directly measuring the distance between the accretion disk and the broadline region clouds. It's like shouting into a canyon and timing the echo to determine how far away the canyon wall is. Once we have this distance, we can combine it with the measured velocity of the gas clouds which we get from the Doppler shift in their spectral lines. With a known distance and a known orbital velocity, a simple calculation gives us the mass of the central object holding those clouds in orbit. Reverberation mapping is a monumental observational effort requiring dedicated monitoring of a single Seyfert galaxy night after night, but its payoff is immense. It allows us to weigh black holes in galaxies so distant that we could never hope to resolve the motions of individual stars. It is a testament to our ability to turn the universe's own physics into a laboratory instrument, measuring a celestial heartbeat to weigh an invisible heart. For decades, our view of these engines was fundamentally incomplete, perpetually obscured by one key component of our own model, the dusty torus. This colossal donut of gas and dust was thought to enshroud the central engine, absorbing most of its visible and ultraviolet light and irradiating it as heat as infrared radiation. This dust was both a confirmation of our theories and a frustrating curtain hiding the most crucial machinery from our sight. To see the furnace, we had to find a way to look through the smoke. That required an eye tuned specifically to the infrared universe, an instrument of such sensitivity that it could capture the faint warm glow of this hidden realm. It required the James Webb Space Telescope. Launched on Christmas Day 2021, JWST is an infrared masterpiece. Its giant golden mirror shielded from the sun's warmth is designed to see the universe in wavelengths of light, invisible to the human eye. For the study of Seyfert Galaxies, this is not just an upgrade, it is a revolution. With its infrared scalpel, JWST can pierce through the obscuring dust of the torus as if it were glass, giving us our first ever direct, unimpeded view of the structures closest to the black hole. The curtain has finally been pulled back. What JWST is revealing is both a stunning confirmation of our ideas and a showcase for the universe's beautiful complexity. With its spectrographs like the Mid-Infrared Instrument or MIRI, we are not just taking a picture. We are dissecting the light from the very heart of the engine. We can see the spectral signatures of hot, swirling silicate dust grains, the building blocks of planets on their final one-way journey into the abyss. We can measure the temperature and density of the gas in the inner rim of the torus, confirming that we are looking at the sun-facing wall of a vast, dusty structure. But the universe is never as simple as our cartoons. JWST has shown us that the torus is not a smooth, uniform donut. Instead, it is a clumpy, chaotic and dynamic stream of individual gas clouds, a cosmic dust storm in constant motion. We can even see evidence for a cold, dusty wind being driven off the disk itself, a flow of material that may be the very source of the torus. We are no longer inferring the existence of these structures, we are mapping them. We are watching the fuel as it funnels from the galaxy down into the torus and from the torus into the accretion disk. We are witnessing the complete cosmic plumbing system of a supermassive black hole live and in high-definition infrared. This newfound clarity extends to the engine's most dramatic consequence, its colossal outflows. While Hubble could see the aftermath of these winds, the glowing ionization cones JWST can see the launch point. Its spectrographs can detect highly ionized atoms like iron that has been stripped of many of its electrons, moving away from the nucleus at incredible speeds. We are seeing the wind as it is born accelerated to a fraction of the speed of light by the intense radiation pressure from the accretion disk. These are not gentle breezes. They are galactic hurricanes carrying more material out of the nucleus every year than is consumed by the black hole itself. By combining JWST's infrared view with data from X-ray observatories like Chandra and radio telescopes like the Very Large Array, we create a complete multi-wavelength portrait of this incredible process. In X-rays, we see the ferociously hot plasma at the very base of the jet. In the infrared, JWST reveals the complex shock waves and molecular gas being swept up by the outflow. In radio waves, we trace the vast plumes of energetic particles as they stretch for tens of thousands of light years far out into the galactic halo. The picture is now undeniable. The Seyfert nucleus is not just a passive consumer of matter, it is an active agent of change, a galactic-scale engine that pumps energy and chemically enriched material back into its host galaxy. Through this concerted effort across decades and across the electromagnetic spectrum, Seyfert Galaxies have fulfilled their ultimate promise. They have become our cosmic laboratories. Because they are relatively close and common, we can study them with a level of detail that is simply impossible for their more powerful, more distant cousins, the quasars. Yet the underlying physics, the central engine of a black hole, an accretion disk and a torus, is believed to be the same. The Seyfert is the accessible working model. It is the proving ground where we test our theories of black hole, growth accretion physics, and the mechanics of jets and outflows. Every photon captured, every spectrum dissected, every orbital path measured in a Seyfert galaxy provides another piece of the grand puzzle of active galactic nuclei. The solutions we find here in these simmering galactic cores can be scaled up to understand the most luminous quasars blazing in the dawn of time. We have progressed from seeing Seyferts as mere curiosities to recognizing them as fundamental pillars in our understanding of the universe. We have journeyed from theoretical sketch to detailed observation, from a ghost in the machine to a fully realized engine of cosmic proportions. We now see the engine with astonishing clarity. We can measure its power, weigh its heart, and map its influence, and this new vision forces upon us the next and perhaps most profound question of all. Now that we understand how the engine works, we must confront the consequences of its fury. What does all of this violent activity actually do to the galaxy that hosts it? Is this engine a creator, a destroyer, or both? And so the intricate machinery comes into focus. From those ghostly smudges on Carl Seyfert's photographic plates, from those strange and defiant spectral lines that refuse to conform to the quiet norm of the heavens, we have journeyed to the very heart of galactic fire. We have travelled through curtains of obscuring dust, navigated the incandescent fury of the accretion disk, and stood at the precipice of the event horizon itself. The puzzle that began as a simple academic curiosity in 1943 has unravelled into one of the most profound revelations in all of cosmology. What Seyfert saw was not an anomaly. It was a signpost, a beacon illuminating a fundamental truth about the universe we inhabit. He had discovered that galaxies could possess a living, breathing, and often violent core. The story of the Seyfert Galaxy is our story. It is the story of how we learn to see beyond the placid river of the Milky Way splashed across our own night sky and recognize the untamed dynamism that truly governs the cosmos. For generations, we imagined galaxies as majestic, but essentially static islands of stars spinning in serene isolation for billions of years. We saw them as finished masterpieces, cosmic artworks hung in the silent gallery of space. But the Seyferts tore that placid portrait to shreds. They showed us that a galaxy is not a static object, but a dynamic evolving ecosystem, and at its centre often lies a ferocious engine of creation and destruction. This journey of understanding has been a testament to human ingenuity, a multi-generational quest to connect a handful of outlying data points to a grand unified theory. Think of the leaps required. From ground-based telescopes capturing faint smatterings of light, we had to build instruments capable of seeing in X-rays and gamma rays the very wavelengths of violence. We had to develop radio interferometry linking dishes across continents to achieve the resolution of a planet-sized eye, just to glimpse the ghost of a jet punching its way out of the galactic core. We had to launch observatories into the cold vacuum of space above the shimmering veil of our own atmosphere to capture the infrared heat signature of that hidden dusty torus. Each technological step forward was a step deeper into the inferno. Each new wavelength of light we learned to decipher was like a new key, unlocking another chamber in this vast cosmic labyrinth. The broad emission lines, once a mere curiosity, became the tortured screams of gas clouds moving at a fraction of the speed of light, whipped into a frenzy by the gravity of an unseen monster. The narrow lines, calmer and more distant, became the ethereal glow of gas fluorescing under the harsh glare of that central engine like fog illuminated by a colossal searchlight. Every piece of the puzzle, from the flickering X-ray signatures to the polarized light scattering off hidden structures, has been painstakingly placed. What we have assembled is a portrait of a process, not just a place. We have uncovered a gravitational heart, a supermassive black hole, whose immense power dictates the fate of the entire galactic continent surrounding it. The story shifted from classifying odd celestial objects to understanding the physics of the most extreme environments imaginable. The search for Seyfert's peculiar nebulae transformed into the hunt for the central engines that drive the evolution of nearly every massive galaxy in the universe, including perhaps the dormant beast that lies at the centre of our very own. We have looked into the Seyfert's blazing core and found a mirror reflecting the fundamental forces that shape our cosmic home. The Seyfert Galaxy, then, is far more than just a bright galactic nucleus. It is a cosmic engine room, a place where the raw potential energy of gravity is converted into light heat and kinetic fury with an efficiency that dwarfs nuclear fusion. This engine does not operate in isolation. Its influence radiates outward, a form of cosmic weather that sweeps across tens of thousands of light years, profoundly shaping the destiny of its host galaxy. This process, which we now call active galactic nucleus feedback, is one of the most critical discoveries of modern astrophysics, and Seyferts are our primary laboratory for studying it. They are the living examples of this cosmic drama unfolding before our eyes. Imagine the sheer power of the radiation blasting from the accretion disk. This isn't the gentle warmth of starlight. This is a celestial blowtorch, an ionizing torrent of high-energy photons capable of sterilizing vast regions of the galaxy. As this wave of energy propagates outwards, it can heat the cold, dense molecular clouds of gas that are the essential fuel for star formation. It can literally boil away the stellar nurseries, preventing new stars from being born. This is negative feedback in its most dramatic form. The central engine in its gluttony effectively shuts down the galaxy's ability to grow, creating what astronomers call a red and dead elliptical galaxy, a relic city of old stars with no new generation to replace them. The Seyfert phase in this scenario acts as a self-regulating switch, a galactic thermostat that prevents the galaxy from becoming too massive. But the story is never so simple. The universe is a place of breathtaking subtlety, and the influence of a Seyfert can be a double-edged sword. While that intense radiation can inhibit star formation, the powerful jets and winds launched from the black hole's vicinity can also act as a trigger. As these outflows plough into the interstellar medium, they create immense shockwaves. These cosmic tsunamis sweep through the galaxy, compressing the very same clouds of gas that the radiation was trying to heat. This sudden violent compression can be the catalyst that kickstarts a furious burst of star formation along the shock front. A Seyfert's breath, it seems, can be both a sterilizing fire and a life-giving pressure wave. It is a symphony of creation and destruction played out on a galactic scale, and we are only just beginning to learn the tune. Furthermore, these galactic winds are not merely internal phenomena. They are powerful enough to blast material clear out of the galaxy itself, enriching the vast dark voids of intergalactic space. The heavy elements, the carbon, oxygen and iron, forged in the hearts of stars and churned through the accretion disk, are not trapped forever within their parent galaxy. They are seeded into the cosmic web, the tenuous filaments of gas that connect galaxies across millions of light years. This means that the activity in one Seyfert galaxy can chemically enrich the raw material that will one day form an entirely new generation of galaxies and stars hundreds of millions of years in the future. We see now an incredible interconnected cosmic ecosystem. Galaxies are not isolated islands, but are fundamentally linked through these powerful feedback mechanisms. These Seyferts are the primary agents of this exchange, the pulsating hearts that pump enriched material throughout the cosmic circulatory system. They are a critical link in the chain of cosmic evolution, helping to explain why the universe looks the way it does today, why some galaxies are vibrant spirals teeming with new life, why others are quiescent ellipticals, and how the vast empty spaces between them became seasoned with the building blocks of planets and people. To understand a Seyfert is to understand the life cycle of the universe itself. And yet, for all that we have learned, the light from these distant cores illuminates the vastness of our own ignorance. We have constructed a beautiful, cohesive model, but it is a model with dark rooms and locked doors, a sketch of the territory where entire continents remain unexplored. The greatest mysteries are no longer about what a Seyfert is, but about the far more subtle and profound questions of why and how. At the heart of it all is the mystery of the cosmic flicker switch. Why is our own supermassive black hole Sagittarius A so profoundly quiet, while the one in NGC 1068, a near twin in mass, rages with incandescent fury? Galaxies move through phases. A tranquil spiral like our Milky Way may have once been a raging Seyfert and could be again. What controls this duty cycle? What sequence of events causes the central engine to roar to life? We believe it is the infall of matter, a sudden meal for the hungry beast. Perhaps it is the tidal disruption of a star that wanders too close, shredded into a stream of superheated plasma. Or maybe it is a grander event, the collision and merger with another galaxy, a chaotic dance that funnels rivers of cold gas down into the galactic centre, overwhelming the black hole with a feast of cosmic proportions. Observing these triggers is fantastically difficult. They are often fleeting, and the moment a nucleus ignites its own brilliant light can obscure the very evidence of the event that sparked it. We are left searching for the subtle clues, the distorted streams of stars from a long-digested dwarf galaxy, the warped gas disks that betray a past collision, the faint X-ray echoes of a star's final scream. We are cosmic detectives arriving late to the scene, trying to reconstruct the chain of events from the lingering chaotic aftermath. The life of a Seyfert appears to be one of violent bursts and long silent slumbers, and we have yet to fully comprehend the galactic clock that governs its waking and sleeping, and what of the engine itself. Our models of the accretion disk are triumphs of theoretical physics, but they are still simplifications. How does magnetism, a force notoriously difficult to model, thread through this swirling chaos? We believe that magnetic fields act like a cosmic centrifuge, grabbing onto the plasma and flinging it outwards in the form of colossal jets. But how are these fields generated and sustained in such an extreme environment? How do they collimate this energy into beams so narrow and powerful they can punch through an entire galaxy and travel for millions of light years? The details are buried in the complex dance of magneto-hydrodynamics, a realm of physics so challenging it pushes the limits of our most powerful supercomputers. Then there is the torus, that crucial obscuring shroud of gas and dust. We invoke it to explain the difference between a Type 1 and Type 2 Seyfert, and the evidence for its existence is overwhelming, yet we have never truly resolved its structure. Is it a smooth, uniform donut, as our simple diagrams suggest? Or is it, as newer models propose, a clumpy, chaotic collection of thousands of individual clouds, a swarming, dusty beehive orbiting the central engine? How does this structure form, and how does it maintain itself against the immense gravitational tides and the ferocious radiation that should by all rights tear it apart? It is a veil that is central to our understanding. Yet the veil itself remains almost entirely unseen, its true nature a ghostly inference. Perhaps the most tantalizing unknown is the role of the black hole's spin. Just as a planet or a star rotates, we believe supermassive black holes must also spin a relic of the angular momentum from all the matter they have consumed. A spinning black hole doesn't just curve space-time, it twists it, dragging the very fabric of the universe around with it in a phenomenon known as frame dragging. This rotational energy is a vast untapped reservoir of power, potentially hundreds of times greater than the energy stored in the black hole's mass itself. Could it be that the most powerful jets are not powered by the accretion disk alone, but by tapping into the spin of the black hole? Are we seeing matter converted to energy, or are we seeing the rotational kinetic energy of space-time itself being converted into a cosmic blowtorch? Answering this requires measuring the spin of black holes hundreds of millions of light-years away, a task so formidable it sits at the absolute frontier of our observational capabilities. These are the questions that will define the next generation of astronomy. They are puzzles that demand not just cleverness, but a new way of seeing a technological leap that will allow us to pierce the dust, resolve the unresolved, and watch the cosmic weather in real time. And those new eyes are now finally being built. On the mountaintops of Chile, the Vera C. Rubin Observatory is preparing to conduct an unprecedented survey of the sky, a decade-long movie of the cosmos. It will catch Seyferts in the very act of flaring to life, giving us the before and after pictures we need to understand their triggers. It will spot the subtle, flickering and variations that betray the inner workings of the accretion disk, mapping its structure on timescales we've never before been able to study systemically. Across the deserts of Australia and South Africa, the square-kilometre array, the largest radio telescope ever conceived, will rise. Its unparalleled sensitivity will trace the jets of Seyfert Galaxies with exquisite detail, mapping the magnetic field structures that shape and launch them. It will detect the faint radio whispers from the earliest, most distant active galaxies, allowing us to see how these engines first came to life in the dawn of the universe. In space, future X-ray observatories will fly with mirrors of unprecedented size and precision, allowing us to probe the region just outside the event horizon. They will measure the relativistic distortion of X-rays using the bending of light itself to map the shape of space-time, and in doing so finally measure the spin of the black hole. We are standing on the cusp of a new era, moving from static snapshots to dynamic films, from inference to direct observation. Our journey, which began with Carl Seyfert and his enigmatic spectra, is far from over. In fact, it may be just beginning. We have peeled back a layer of reality only to find a universe more complex, more interconnected, and more violent than we had ever dared to imagine. We have learned that the centres of galaxies are not points of quiet gravitational stability, but the sites of nature's most efficient and powerful engines. We thought we were studying a peculiar class of galaxy, but we found ourselves studying a fundamental process in the life of the cosmos itself. Look up at the night sky. See the quiet stars, the faint milky haze of our own galaxy. It feels peaceful. It feels eternal. But that tranquility is an illusion of distance, a product of our fleeting human timescale. Hidden in the hearts of those distant faint smudges of light are gravitational furnaces raging with the light of a trillion suns. They are the cosmic lighthouses, the pulsating beacons whose light tells a story of galactic birth, evolution, and death. They are the unpredictable, untamed hearts of the cosmos, and in their rhythmic, violent pulse we hear the true dynamic heartbeat of the universe. The mystery Seyfert uncovered is now our quest, a journey that continues with every new image, every new spectrum, and every new question we learn to ask. The darkness still holds its secrets, but for the first time we can begin to see.